Okay, for de Broglie, the concept, the quantum concept is light is actually two things. It's particulate and it's wavelength. Actually, any subatomic particle would be both particulate, a particle, and wave-like at the same time. This is the only question, if you look at this formula closely, too bad I crossed it out, where we have wavelength and velocity. If you ever have a question that has both wavelength and velocity, this is the only possible equation to put it in, okay? So let me just rewrite this equation one more time. Lambda equals hm over u. Usually the variables that we're asking you for are lambda or u, the velocity, okay? Everything else is pretty much a constant. So this is Planck's constant, that's a given. Okay, this is a given constant, that's a given. M, that could depend on what it is. So it could be the velocity of the mass of a particular entity. If the entity is not given, let's say we're talking about a hydrogen atom, then the mass of what would you put there? Not necessarily the atomic mass. No, molar mass. Mass of electron is usually what we're talking about. So usually this is the mass of an electron, typically. Unless it says it's some other particle specifically. So if it just says a hydrogen atom, it means the electron on the hydrogen atom. Unless we specify, for example, we say it's a proton, or it's a neutron, or it's a baseball. Unless we specify, which we could likely do, the default is the mass of the electron. Okay, that's it, plug and chug. Next. Let's do Rydberg now. Rydberg. Rydberg, some other classes, do you use Balmer in your other class or you use Rydberg? You have no idea. Okay, use this equation that I'm about to give you, okay? The change in energy is the Rydberg constant, 1 over n initial squared minus 1 over n final squared equals h nu or hc over lambda, okay? So this equation, it's two halves. It's really this side and this side. And really the change in energy is the absolute value. Okay, so the reason you know it would be this equation, if we talk about orbits or levels, n goes from 4 to 2 or from 3 to 7, any sort of orbit change, it can only be this equation. That's it. There's no options. So if you had to set something up, you and your friends can pick up n, pick n values. They're whole numbers. Somebody pick a number for me. 7 and 6. Too late. This is making me crazy. Wow, you guys are excited. I'm glad. Okay, let's say it goes. You want to go from 6 to 7. Does that sound fun? Okay. So if it goes from 6 to 7, is the energy value going to be positive or negative? Positive being is energy going in or out of the system? In. To go up, meaning from 6 to 7, it's going in. So you'd say, well, the change in energy is the Rydberg constant, which should be given to you, 2.179 times 10 to the 18th joule seconds, 1 over n initial squared minus 1 over n final squared. And then if you wanted to set that equal, if you wanted to find lambda, that's hc, h 6.626 times 10 to the minus 34. This is not joule seconds, that's just joules. This is joule seconds. Times c, 2.9979 times 10 to the 8th meters per second over, for example, in this case, lambda. So in this case, I could solve for E if I wanted to, or I could actually set it equal to the bottom part and solve for lambda. Depends what you're asked for. You could be asked for the change in energy. That's all you need. If you need lambda, do that. You could also be asked for frequency. That's just h nu. So you just set it equal to. In this case, this top line would be a positive number, meaning the energy is going into the system. And then you can solve for lambda here to find the wavelength. Would you be able to see this wavelength? Is this visible light or not? This is not visible light. Visible light, there's only a couple scenarios when it goes from 3 to 2, 4 to 2, or 5 to 2. You know those are going to be visible, because that's what's called the Balmer series. It's visible light. If it's any other transition besides those, it could be per chance visible, but usually not. So you would probably get probably not here, because it's not going from 3 to 2, or 4 to 2, or 5 to 2. But it could be randomly. All right, that's it. It's plug and chug. That's it. You're looking for orbits. Let's go to the next one. Any questions on this? Before I move on? Yeah. Great question. Lambda is going to end up being in what units? Meters. Yeah. What units will this be in? Energy. Joules. So always SI units, but we might ask you in nanometers, so you'd have to convert. That's pretty common. We like nanometers. Yeah. How do you convert to nanometers? 1 meter, you need to know all your SI units. It's 10 to the 9 nanometers. Make sure you know all those SI units. That's in your reader, or in your textbook in the beginning, but in your reader right in the beginning, in the introduction part, it has all the SI units I want you to know. Okay? It looks something like this. It's called SI prefixes on page 3. Okay? Nano is nano, kilo, giga, things like that. Milli or centi are going to be the ones you see most commonly. But any of those are fair game, really. Okay. Yeah. Yes. Question somewhere. Hi. You'll probably have to show me if there's something to switch. It's probably just an illusion. Meaning, if it'll feel like switch, but you should show me so we can kind of work it through if there's a specific example. There's also one, I think, on practice final or exam 2 that feels that way. You'll see probably a practice final, because nobody's asked me yet this quarter. That where it feels like you switch it, but you're not. It's just an artifact of the map. Okay, cool. Let's do some quantum, no, let's do uncertainty, because that's also a formula. Uncertainty. Okay, the form that I consider kind of unusable looks like this, at least for our level of class. Okay, we rewrite this as just, we're looking for x, a distance, a length, a position, something like that. P is just a mass times a velocity, that's momentum. You're going to be given in the question a percentage. Okay, some sort of, it'll be associated with the accuracy or precision or something like that. And just set this equal to h over 4 pi. It'll be mathematically a little easier. And then let me underline, we'll usually ask you for either x, position or distance, and then velocity. One of those two, those are your two variables. One is given, the other one's solved for. Okay? Everything else is a constant. So really, and then when you solve for one of these two things to know about them. One is, it's when you say find the velocity, that's not the actual velocity, it's really the uncertainty in the velocity. Same for the position. The other is, if you're doing a calculation for something that's small, microscopic, then you're expecting a relatively, what kind of number? Large or small? Large, yeah. If you're doing this for something macroscopic, something you can see, you're expecting a relatively small number. Okay? All right. So this is just plug and chug. The mass, it's either given, or say it's something like the hydrogen atom, it is what? The mass of? Usually an electron. Okay? Now, so if it's something of the, we're assuming it's electron, unless it's explicitly given. Say, you want to know for a neutron, or some sort of particle, or some entity, or whatever, and they give you the mass, that's fine. But if it's not given, it's talking about hydrogen, they mean the electron. Everything else is a constant. This is just an artifact of the uncertainty, this percentage here, and that's a number given in the question. How do you know if it's this sort of problem? Usually you're going to see the words either uncertainty, precision, accuracy, something like that in the question. That'll lead you off. It's this sort of thing. This is literally plug and chug again. So, should feel straightforward. Everything else, everything I'd recommend in SI units here. All the previous formulas, SI units. All right, next. Any questions on that? Okay. If you have a specific problem, we can do it a little bit later. All right, now let's actually go to quantum numbers, and we'll probably bleed into some of these other topics here. Quantum numbers. Oh, there's a question, yes. Mass, yes, put mass in kilograms, that would be SI units, correct. Good, good. Okay, quantum numbers. So let me just go through a variety of types of questions you could be asked. So let's say one type of question is N, L, M sub L, M sub S. Let's say I give you something like -1 and 3. And I want all the other numbers. This is one kind of question. So let me get a different color pen here. Okay, let's start off with M sub S. Okay, these other two are given fixed. What are all possible values for M sub S? Yeah, plus or minus a half. That's it. I mean, both of those. Okay, L, what's the largest L could be? 2, yeah, because N is 3. Okay, now what L equals 2, will it give this value of M sub L? Yeah, because it'll go from plus L to minus L, so we're 2 down to -2. Okay, what else could it be? 1. Will 1 give a -1? Yeah, because it goes from +1 down to -1. So 1, 0, -1. Could this be 0? For N it could be 0, but for M sub L? No, because a 0 would not give a -1. So don't write a 0 there. That's one type of question. Another type of question would be, say, this kind of mixes with electron configuration a little bit. But let's say for, let's see, I got my periodic table right here. Let's just say for boron. All right, for boron. No, yeah, sure, whatever. No. Nitrogen, let's do nitrogen. 1s, let's write the electron configuration for nitrogen. 2s, and then 2p. Okay, it's 1s2, we're doing nitrogen again. 2s2, 2p what? 3. So if you don't know how to fill it in, it goes like this. You singly fill first. This is called Hund's rule. And we got up to 3, and then you would doubly fill there. So you can go 4, then 5, then 6. Point it down. Okay, there's N, a nitrogen electron configuration. Common type of question. Let's say I circled this electron right there, and I wanted all 4 quantum numbers. And you'll see this on practice exams, worded in slightly different ways. What's N for that electron right there? 2, because it's 2s. What's L? Not 1. If you say 1, 0. How do you know it was 0? S. You don't know this, you better know that S, P, D, F goes with. This is a super common thing that people mess up. Which number goes with what letter? Okay? You don't be that person. Let the other crazy people be those people. Okay? I would write this on your exam in the first 10 seconds of starting the exam on the back page, just so you can remember. You can always refer back to it. M sub L, what would M sub L be? 0, because L is 0. M sub S? Yeah, it's not plus 1/2 in this case, because it's definitely pointed down. There we go. Do you want to do another one? You feel okay?
Another one.
Okay. They're not harder or easier. Somebody want a harder one. It's just this. You want to do this one? I don't care. Okay, yeah, question. While this person's asking a question, you can start filling in this. Okay, what's your question? Where'd you go? Oh, they took it back. I don't see them. It was you. Okay, hi. Okay, yeah, take the spotlight. How did I got these 4 numbers? How I got M sub S. If it's pointed down, which it is, it's -1/2. Symbolically, a down arrow means a -1/2 value. Symbolically, an up arrow means a value of +1/2. That's it. These are all +1/2s for M sub S. That one right there that I circled is a +1/2. Okay, what's N? 1 because 1s L, 0 because it's S, and M sub L, 0 because L is 0. There we go. Yeah? How did I find M sub L? It's not from any of this, it's always from L. If L is 0, M sub L goes from negative 0 to positive 0, which is just 0. Yeah. Is that okay? If L was 1, M sub L would either be negative 1, 0, or positive. Is that okay? Okay. Yes? It depends. Is it all three? Minus 1, 0, plus 1? If you don't know anything else, yes. If L was 1, M sub L is all three of those values. It depends on the question. Yeah. Okay? Ready to go on? Yes. Okay. Would you always have a diagram for M sub S or not? Well, here you didn't, so I had to guess both values. But if you have an arrow, that tells you which value it is. If you don't have an arrow, you have to put both values in. Yeah. Okay, that's another type of question. Next, another type of question that you could get for quantum numbers is say n equals, how hard do you want this? Test it, a 5 would be really hard. I mean a 6 would be really hard, but this would be hard for exam. I wouldn't put 7 on an exam. So, okay, let's say n equals 5. I want the number of electrons that were spin down. Okay, how many electrons for n equals 5 are spin down? Then what do? Well, you say, so all of these are common quantum number sort of questions. You say L. What's the smallest L could be? The smallest would be 0. 4 would be the largest. 2, 3, 4. Okay? So those are all the possible values of L. Remember, above the line is given. So below the line, these are all possible values. Then what you do is you'd say M sub L for this type of question. So you write all the M sub L's for each individual L. So for L equals 0, M sub L is just 0. For L equals 1, somebody just asked me, it's 0 plus or minus 1. If L is 2, then it's 0 plus or minus 1 or plus or minus 2. This is not an addition or something, these are just a list. Okay. If L is 3, then it's 0 plus or minus 1 plus or minus 2 plus or minus 3, then that's it. If it's 4, then M sub L is 0 plus or minus 1 plus or minus 2 plus or minus 3 and plus or minus 4. So the L bounds the M sub L from plus or minus L. Okay, then what you do, next column, you go, this is all to solve this one question. The number of values of M sub L. So you gotta literally count the number of values. So for example, when L equals 0, there's one M sub L value. When L equals 1, that goes with that one. When L equals 1, there's 3 values of M sub L. When L equals 2, there's 5 values. When L equals 3, there's 7 values. When L equals 4, there's 9 values. Does that make sense? Just counting the values? Okay, the number of values represents what? The number of orbitals. Yeah. So number of values, if you didn't know that, represents the number of orbitals. Okay? All right. How many electrons go in each orbital? 2 maximum per orbital. So if there's 2 maximum, how many spin down per orbital? 1. There's 1 up, 1 down. Okay? So, how many spin down electrons are here? 25. You just add these up. There's 25, I added all those 5 values up, 25 that are spin down, 25 are spin up, or a total of 50. 2 per orbital, and there's 25 orbitals in this situation. See how it works? Okay, you and your friends can pick any number. The reason on my test, I wouldn't really go above 5, is you just have so many things here you're adding up, it gets ridiculous. Okay, any questions on this? Did you say something? 25. 25 spin down electrons. There's 25 spin up, and there's 50 total. All right, there's probably other examples. That's all I can think about off the top of my head at this moment. Okay, next. Drawing orbitals. Let's do, oh yeah, that's another kind. When you draw orbitals, there we go. Do you want me to just do a couple random orbitals? Is that helpful? Yeah. Yes? Uh-huh. How did I get these numbers? That's up from m sub L. Yeah. When you're counting m sub L, that represents orbitals because m sub L is orientations of orbitals. So you count each one, you have the total number. So for example, this, when L is 0, there's one orbital, that's an s orbital. When L equals 1, that's a p orbital, there's 3. When L equals 2, that means d, there's 5 d orbitals. When L equals 3, that's an f orbital, there's 7 f orbitals, and then etc. Is that okay? Cool. All right, now I don't know what we're doing. Drawing orbitals, okay. So somebody, which one do you want to draw? S, P, or D? D, let's do a D. Do you want me to make up one? Let's do DXZ. And what number do you want here? A 3 or a 4? Okay, I heard more 4s. Okay? So, a 4DXZ. So, the subscripts tell you the graph axes. So, this is the XZ axis. Okay? And then a d orbital looks like a 4-leaf clover. So let's draw one. 1, 2, 3, 4. Okay? 4-leaf clover. Then I'd ask you about the nodes. Let's ask you about all this. N equals what value? 4. Is that? L? 2. Okay. Make sure you're sure. 2. Okay, what else could I ask you? Nodes. How many nodes? That's n minus 1 or 3. Or minus 1, 3. Okay. 2 of them are called what? Yeah, angular nodes. And those are just basically cutting this in half. In this case, they're the axes. Okay. Those are angular nodes. Where's that last node? It's a circle, and it's called a radial node. By the way, this is also a common type of final exam question. And good that some of your buddies are here, because you can study for example, definitely the final together, because we're all having the same final. Okay, did I get all the nodes? I think I did. 3. One other thing that you can do, not all, we're more into shading when we get to chapter 10, but for now you can do some shading. Let me get a different color, I'll do blue. Opposite sides have the same shade, and then you flip shades at a node. There's the shading. Some people like plus and minus instead of shades, so I don't know how your particular instructor is if you're not with me. Yeah? Yes. Good. Why? Anybody? Why is it L2? Okay, people mumbled a lot of stuff. Let's assume they were right. I have no idea. I don't even know what the heck you're talking about. But this that I'm making you, please write this on your exam when you start. Okay? So you do not forget that. Yeah, that was, okay, several questions. First, yes, have a little. Okay, hold up. So you want to do, let's just do this, a 3dx squared minus y squared. If you wanted to do that, then it's on the xy axis, but in this case, they're on axis. Like this, not off. The squares are the mnemonics, that it's like this. Then the 2 angular nodes are like this. They bisect it, just like the other one. 2 nodes, those happen to be angular nodes. Is that okay? Okay, there's somebody behind you, yes?
Is there a reason why you shaded that part as opposed to doing the full side?
Why did I not start shading here? Random. Yeah. Yes?
Can we do
Oh, that's a good idea. Okay. Oh, Ray, I moved it. Okay. Do you want, oh, but if I ask you which orbital, then that wouldn't work. Okay. Now in this case, I could give you something harder because I'm drawing it for you. Okay, if I didn't want to do that. So now I can care less how hard it is. Oh yeah, let's just go crazy. Okay, I'll give you a moment, see if you can write down this orbital name, which is called the orbital designation, is what we call the orbital name. So meaning, is this 2s, or 5dx squared minus y squared, or whatever. Okay, what's that orbital's name? I'll give you a moment. So we could shade it too for fun. It would be shaded like that.
Yeah, but it's only z-axis.
Give you another 10 seconds.
14z. But there's no node, so...
There could be a node in the center, but I don't have to tell you that.
Oh, yeah.
I'll answer that question at the end. Got it. Okay. First of all, SPD or F? P. Okay, close. PZ, and the first number is? How many nodes did you see? 1, 2, 3, and of course this is born with one here. I wouldn't have to draw the middle one because it's born with an angular node. Just like the D is born with 2 angular nodes, the S is born with how many angular nodes? 0. Yeah, the S is born with 0 angular nodes. This P's always have 1 angular node, so it has to have 4 total nodes here. 1, 2, 3, and 4. So it's a 5 because the nodes are n minus 1 or 1 less. N is 1 more than the number of nodes. So it's a 5 PZ. Any questions? Yeah. How did I know it was a P? Because a P looks like a 2-leaf clover. A S is a sphere. A P is a 2-leaf clover. A D is a 4-leaf clover. And then F's get really complicated. They could have multiple lobes, but generically, you might say there's 8 leaves on an F. By the way, if you're in my class, I sent you on SmartSite a website that actually has an orbital viewer. You can type in NLM sub L, and it'll pop out the shape of that orbital. If you want to play with that, it even shows you where the nodes are. You can do a cross-section of it. It's pretty cool. One of my TAs showed it to me. Okay, that's it with drawing orbitals. I have a video, I think it's called Drawing Nodes and Orbitals. I'd recommend that one. If this is totally alien talk to you, watch that YouTube video. Okay, and I posted it on SmartSite. Yeah. Why did you shade? It always has shades, so the opposite sides are shades. There are shades. And basically, anytime there's nodes, there are shades. Yeah, that's the best way to put it. If there's a node, there must be shading. Now, I'm not really watching too carefully on shades for exam 2, but on the final, it'll be a big deal. So I'm just including it here for fun. Yeah. If you did the shading here, again, it doesn't matter which 2 you shade as long as they're the opposite side of each other. So it'd be right, left, or top, bottom. That's right. Cool. Yes? Why was there 5? Here it is. Why was this 5? Because I counted 4 nodes. 1, 2, 3, 4. And nodes is n minus 1. So if there's 4 nodes, then this is 5. Okay? Cool. All right, I gotta keep it moving. We're doing E configs, and then we'll finish chapter 7. electron configurations. So there's two ways we can do electron configuration question. Basically, one way is I can give you the element, which is the common generic way. So you probably see more examples of that. The other way is I give you the electron configuration, you tell me what the element is. And let me see if I brought my thing that I'm looking for. But let's try one. I want to try a couple. So we'll try bromine. I want to try phosphorus. No, not phosphorus. I want to try aluminum +1. I want to try copper 2+. And then I want to try for the last one. You can get started ahead of me. Go for it. For the last one, I want to find a trickier one. So I gotta think for a second here. Go ahead and start ahead of me for sure. Till I find an ugly one for us.
I'll take like
Oh yes.
I'll take like 2.
I love it.
Like counting, right? Yeah.
Why do you call me?
Okay, that's good. All right. So let's, if you're working ahead with your buddy, that's fine. Go ahead and work. Go through all these if you want to. There's one more type of question. I'll do that at the end of this. So for bromine, the previous noble gas would be argon. And then you go, okay, to go to calcium, it's 4s2. Then you go through the 3D block. So you go through 3D10. That takes you to zinc. And then the bromine is on the 4p level. And there's 1, 2, 3, 4, 5 of them. Look like that. Okay, aluminum +1. So aluminum +1, I'm really doing which one? I'm really doing magnesium. So that's just magnesium neon 3s2. That's it. Copper 2+. Now here's a tricksy one a little bit. So I think it'll be easier to do copper neutral first in this case. And the reason that whenever it's a transition metal, I think it's a little easier to do the neutral first. So let's do copper. That's previous noble gases, argon. And then we go 4s something, 3d something. 4s what, 3d what? 1 and 10, yeah. This is one of the exceptions. Somebody asked me to cover this. One of the exceptions of the transition metals that pretty much, as far as I know, all instructors cover because you have to know this stuff. And the 4th column and 9th column of the transition metals, that's the chromium column and the copper column, it half fills the S's and then fully fills, and then puts the rest in the D's. So it half fills the S's on the chromium column and the copper column and fully fills the D's. Or fills the rest of the D's, I should say. Now, for copper, here's our second exception. For copper +1, that's going to be argon. Which one is lost? Yeah, now normally you lose from where you just filled, which would be the D's in this case. But for a transition metal, it's going to lose the S's first, 3d10. So copper 2+ is argon 3d9. It's losing the second one from now the D's. First one was from the S's. Okay, for the last one here, what I'd recommend is not work backwards. What is the easiest is to find radon and find its Z value. What's the Z value? 86. That's the Z value, number of protons, and if it's neutral, which it is here, number of neutrons. You add 2 to that subscript, and you add 14 to that. What's that equal to? 102, which is what? Yes, no. Nobelium. Okay? So, nobelium, number 102, is your answer. That's the easiest way to work these, is to add the electrons. There's one more I wanted to do that I just thought of. Let's say I give you phosphorus, and I could have you draw some of the alternate diagrams. Like the orbital diagram, you could say phosphorus is neon, and then either boxes or lines. The next one is the 3s, and then the 3p. So this is the one way to draw. You go 3s, 2, and 3p, 3. 1, 2, 3. So just an alternate electron configuration. You could also draw this vertically. That's the orbital energy level diagram. So the same diagram but vertically. And you're going to use this a lot when you get to chapter 10. We'll do this a lot. 3s2, 3p3. So those are both equivalent electron configurations. The top are condensed electron configurations. This is the orbital diagram, and this is the orbital energy level diagram. Why? Because you're showing the orbitals specifically. Yeah? The core electrons you usually don't have to show. The question is, where do you show them? It depends. You have to read the question carefully. So if you were going to show them on either, you just put them before. So before that is a 2p. Before that's a 2s. Before that's a 1s. So we have asked you to show before. 1s2, 2s2, but the question is explicit. You'll see, I think, last quarter's exam or last year's. Look at the practice exams, you'll see it. 2p6, 1, 2, 3, 4, 5, 6. So yeah, I'll try to be really specific if I want the core electron.